Hello and welcome to the Emirates Society of Emergency Medicine Emergency Ultrasound Lecture Series. My name is Rasha Buhamed and we will be talking about basic ultrasound physics and knobology. A basic understanding of ultrasound physics is essential to reliably acquire quality images and provide accurate interpretation. While many modern point-of-care ultrasound systems limit the operator's ability to adjust the various settings, there remain a number of important features that allow users to customize and indeed improve imaging. The objective of this talk is to review basic ultrasound physics, the basics of an ultrasound machine, probe selection and image orientation to help customize and improve imaging. I promise I'll try not to go through complicated physics formulas. I will try my best to keep it as simple as possible and review very important high-yield physics concepts to help you understand point-of-care ultrasound. So what is ultrasound? Ultrasound is a mechanical longitudinal waves that propagate through a medium and interacts with the tissue it passes through. Sound waves are divided into three different types based on the wave frequency. Audible sounds are frequencies between 20 Hz and 20,000 Hz, while infrasounds are any waves that are less than 20 Hz, while ultrasound is defined as waves with a frequencies greater than 20,000 Hz. Ultrasound waves have specific characteristics, including the amplitude, period, wavelength, frequency, and velocity. And two very important wave characteristics that we should go through is understanding what is the frequency and the velocity. We'll start by discussing frequency. Frequency is defined as the number of cycles or wavelengths per unit time. It is measured as cycles per second, and the unit of frequency is hertz. Frequency is a major factor in determining the depth of beam penetration. The low frequency has less resolution but has more penetration, therefore can image deeper structure. While the higher the frequency, the more the resolution, but it has less penetration and therefore the image is going to be shallow. Another important wave characteristic is propagation speed, which depends on the medium. The velocity of sound wave varies with the density and the stiffness of the medium. The greater the stiffness, the faster the wave travels. Therefore, the velocity of sound is low in liquid, highest in solid, and very little in air. The average velocity of waves in soft tissue is about 1540 meters per second. And this is the value assumed by ultrasound machine for all soft tissue. When a sound wave encounters a material with a different density, which is known as acoustic impedance, various things can happen to the sound wave. Acoustic impedance depends on the density of the medium and the propagation speed of the wave. But as the speed between the soft biological tissues varies only slightly, impedance depends mainly on the difference in the density. The greater the difference between the acoustic impedances, the larger will be the echo. In this diagram, we're going to demonstrate what happens to the ultrasound waves when it travels through two different mediums. So medium 1 and medium 2, the ultrasound waves travels through the medium. Once it reaches the surface of the border between the two different mediums, the ultrasound wave can attenuate. Attenuation occurs due to the absorption of ultrasound energy by conversion to heat. The attenuation of the sound wave is increased at a higher frequencies. So, in order to have better penetration of deeper tissues, a lower frequency is used. The sound wave can also be reflected. The reflection occurs when part of the sound wave is reflected back to the transducer and is detected as an echo. The time taken for the echo to return and travel back to the transducer is measured and is used to calculate the depth of the tissue interface, causing this echo. Sound wave can also be refracted. Refraction is the bending of wave beam when it crosses the interface of two materials with different propagation velocities at an oblique angle. Similar to the light waves, this is also known as the Snell's law. The brightness of the image produced by the ultrasound machine, or what is known as echogenicity, is determined by the rate of reflection and attenuation of the sound wave. When the sound wave reflects more than it attenuates, the image produced will be brighter. This is also known as hyperechoic or white. And for example, this happens when the ultrasound wave interacts with stones or bones. On the other hand, if larger part of the sound wave attenuates and very little is reflected, this is going to produce an anechoic or darker image or hypoechoic image. For example, this is what happens when sound wave interacts with tissue and fluid. Most ultrasound machines have 256 shades of gray, corresponding to the returning amplitude of a given ultrasound wave. As you can see here in the image demonstrated, black is anechoic or hypoechoic, there's no echoes returning, while white is hyperechoic, that produces strong echoes because they reflect more waves back. Acoustic windows allow sound waves to penetrate into the body, so that's very helpful in imaging. Good acoustic windows include the liver, the spleen, a urine-filled bladder, or any fluid-filled structure, while poor acoustic windows include gas, which is in the lungs and the intestines, as well as strong reflectors like bone. How do we produce ultrasound images? Ultrasound images are produced by what is known as the piezoelectric effect. Piezo means pressure, electrics mean electricity. So electrical current causes vibration of the crystals in the ultrasound probe, which generates wave that goes through the tissue, and the returning echoes of the ultrasound waves deforms these crystals, which in turn are processed by a transducer and gives us images. There's a lot of fancy post-processing that happens in the ultrasound machine itself. Using the principle of reflection, an ultrasound machine can calculate the distance and depth of a structure by measuring the time it takes for an emitted ultrasound beam to reflect back to the source. This is the same principle that is used in the sonar submarines. When the ultrasound wave goes through a shallow object, it returns faster to the ultrasound crystals, and this is going to form what's known as the near field, or the upper part of the screen. On the other hand, when the ultrasound waves travel deeper, the returning echoes take longer to return to the crystals, and this is what's going to form the far field or the image further away or lower in the ultrasound screen. There are three basic imaging modalities that can be used by ultrasound: the B mode, the M mode, and the Doppler mode. In the next few slides, we are going to briefly go through these imaging modalities. The brightness mode is what we use for diagnostic imaging. B mode scanning converts the amplitude of ultrasound wave into an image by using a grayscale converter. Most scanners now display images with up to 256 shades of gray, allowing the visualization of subtle differences within tissues and structures. The M mode or the motion mode plots a wave that demonstrates the motion of tissue structure of interest relative to the transducer image plane, which is the white line that crosses the structure on a vertical axis and time on a horizontal axis. This is often used simultaneously with the B mode scanning to study the motion of valves or to measure and document fetal cardiac activity. Doppler or D mode is an imaging modality that relies on the principle of Doppler frequency shift. Doppler ultrasound can differentiate movement of the reflected ultrasound waves towards or away from the probe. This is represented either by color change, which is known as color Doppler, that is demonstrated on the left side of the screen, or by an audible or graphic peaks known as spectral Doppler, which is the image on the right side of the screen. In the next few slides, we will go through some basics of the ultrasound machine and go through very important knobs and buttons. One of my friends told me once that ultrasound machine is exactly like a car. There are different types of cars, but they all have basic switches that are similar. So the 5 important buttons in an ultrasound machine that we're going to go through is the power, probe selection, the depth button, gain, freeze, and save. It's important that you go back to your department and check your ultrasound machine and get familiar with these buttons, because that's going to help you with your image acquisition and getting proper good quality ultrasound images. So the power button is used to turn the machine on and off. I know this sounds very simple, but it's very important because if you don't know where your power button is, most of the time the machine is not going to switch on and you will be frustrated and therefore not use your ultrasound machine when you take care of patients in the emergency department. Make sure that the ultrasound machine is actually plugged into electricity, because most of the ultrasound machine, the battery life is short, and if they're not plugged in, even if you're trying to switch the power button on, it's not going to turn on. So make sure it's connected and make sure that you know where your power button on to switch this ultrasound machine on. The second is probe selection. Every ultrasound machine has different number of probes that are available, and you will find, this is an example of the Sonosite, and you will find they have 3 different probes that are attached to one machine. And in order to select the probe, you click on the button corresponding to that probe. Otherwise, you will be scanning the patient, but you won't be getting any images if you don't select the appropriate probe. The next is the depth button. Adjusting the depth is very important when you want to improve the quality of your image. And to find that in this machine, you will find the button labeled depth. And the depth button you can use to, if you select the up, it's going to make the image more shallow, and if you select the lower one, it's going to make the image deeper. The gain button is important to adjust the brightness of the image that you produce. In this machine, you will find 3 different gain buttons that you can use to adjust the brightness of the image. The near field gain that will adjust the brightness in the top half of the image. The far field gain that will adjust the brightness of the bottom half of the image, and the overall image brightness. The freeze and save. This is very important when you want to document and save your studies. So you will find a freeze that will just freeze the image that you acquired. You can use this pad to scroll back a few seconds to choose the best image you want to save. And you click on save in order to store the image you acquired into the ultrasound machine. So these are the 5 basic buttons that you can remember and be familiar with to help you with getting good quality ultrasound images. In the next few slides, we will review the number of ultrasound transducers and the difference between these transducers. The curvilinear or abdominal probe is a low-frequency probe. It's commonly used for various exams including the FAST exam, aorta, gallbladder, renal, bladder, and uterus evaluation. The probe itself has a larger footprint. It is a low-frequency probe, therefore it is used to image deeper structure. It has less resolution, but on the other hand has a wider field of view. A vascular probe, or also known as the linear or high-frequency probe, is commonly used for IV placement, central line placement, abscess and cellulitis evaluation, foreign body evaluation, as well as ocular exam. It is a high-frequency probe, and as you can see, the footprint is flat, and therefore it's called the linear probe. Because it's a high-frequency probe, it images shallow structures only, because the penetration is not very deep. The advantage of a high-frequency probe, it gives us higher resolution. A cardiac or a phased array probe is also a low-frequency probe. The advantage of this, it's commonly used for echocardiography because the footprint is small enough to place it in between the ribs to get a good images of the heart. And it's also very good for moving objects, example, the beating heart. It has a narrow field of view. The last probe we're going to discuss is the intracavitary probe. It is a high frequency but a curved footprint. It's commonly used to evaluate the uterus and ovaries using a transvaginal pelvic exam, for early pregnancy evaluation, as well as intraoral looking for abscesses, for example, peritonsillar abscess. When discussing the different probes, you will see when we go through all of the ultrasound applications, it's very important to understand the transducer orientation. And the transducer orientation depends on the probe marker. You'll see in this machine, the phased array probe as well as the curved probe, they have a specific probe marker that will help you understand the orientation of the image. When we do point-of-care ultrasound, and most of our imaging, the probe marker usually points to the patient's head or cephalad or to the patient's right. And that's a very important point to keep in mind because that's going to help you understand the probe orientation and the image acquired. To understand image orientation, it is important to remember that the area nearest to the probe is at the top of the ultrasound screen, while the area deeper to the probe is at the lower part of the ultrasound screen. This is what we know as the near field and the far field. The probe marker corresponds to the blue dot on the screen. So if the probe marker is towards the patient's head, the left side of the image corresponds to the top, while the right side of the image corresponds to the bottom. Depth is indicated along the side of the ultrasound image, and that is important for you to correspond how deep the structure you are trying to acquire. For example, the total depth in this ultrasound image on the right is 13 centimeter. Fine-tuning your images. It is important to choose the correct transducer. We understand that the high-frequency probe is important to image shallow objects because it gives you better resolution. While if you want to image deeper structures, you choose the low-frequency probe. You need to adjust the depth to center the organ of interest or the structure of interest into the middle of the screen to give you the better resolution. And in this video is a demonstration of how when they're adjusting the depth of the screen to keep the image of interest in the middle of the screen. It's also important to remember to actively adjust the gain. You don't want the image to be too dark or you don't want the image to be too bright. And finally, remember, you should obtain 2 different planes for every structure that you scan, because ultrasound images are 2-dimensional representations. A comprehensive ultrasound studies require scanning of every organ or structure in 2 different planes. I'll give you a second to let me know what is wrong with this picture. This is an ultrasound machine that has a urinal hanging on it. So this is one of the pictures that was taken by my colleague Scott Glazier, and he emailed us all to let us know he was extremely mad because we did not take a good care of the ultrasound machines. So remember, these machines are expensive, so keep your machines clean, and you can clean the machine and the probe with soft cloth. You can use the recommended disinfectant on the probes. Do not use any commercial cleaners or alcohol on the machine or the probes. And do not drop the probes, run over the cords, or park the machine in traffic, because that's just going to ruin the ultrasound machine and therefore will be out of service and you will not have this valuable technology with you. So how can you get better? Remember to use your ultrasound probe whenever you get the opportunity on your patients. Whenever you're getting a comprehensive study, perform your bedside ultrasound. This is how you're going to get better, and this is how you're going to get more confident. Here are some of the references that I used for this talk, and thank you.